When you watch a massive chemical rocket tear through the atmosphere, it looks like the absolute peak of human engineering. But behind that wall of fire and noise is a quiet truth. You're actually watching a machine struggle against its own design. This diagram illustrates a physical reality known as the rocket equation. To escape Earth's gravity, you need a tremendous amount of fuel. But that fuel is heavy. To lift that extra weight, you have to add even more fuel to your vehicle. By the time that vehicle actually reaches orbit, those massive fuel tanks are completely empty. They become dead weight that the spacecraft now has to drag along for the rest of its journey. Because we have to haul all that mass, our top speeds are capped. It still takes around 6 to 9 months just to reach Mars, and reaching another star system within a human lifetime remains impossible using these methods. To actually explore the deep cosmos, we have to stop relying on controlled explosions. We need a way to stop burning physical fuel entirely. Engineers are already rolling out the first major workaround. Instead of combustible liquids, engines like ion and Hall effect thrusters use electricity to generate thrust. As this schematic shows, magnetic fields inside the engine chamber trap electrons to create a swirling plasma. The system then uses electrical power to accelerate charged particles, usually xenon gas, out the back. The physical force pushing the spacecraft forward is tiny, about the same pressure as a single sheet of paper resting in the palm of your hand. But while a chemical rocket burns out in minutes, an ion engine can fire continuously for years. NASA has already proven this works on deep space missions. You can see the intricate metallic core of the Deep Space One probe here, which use early ion technology to successfully navigate the solar system. Spaceflight is changing from a violent, short-lived sprint into a quiet, continuous glide. Over years of constant acceleration, that tiny push builds up to speeds that chemical rockets cannot match. But gliding takes time to build up speed. If we want to move quickly from the start, we need extreme energy density. That is what nuclear propulsion provides. A nuclear thermal rocket uses a miniature reactor to heat liquid hydrogen to extreme temperatures, blasting it out the nozzle. This generates massive thrust at twice the efficiency of the best chemical rockets. For astronauts, that efficiency translates to safety. A nuclear engine could cut the travel time to Mars in half, meaning crews would endure less radiation exposure and psychological strain in the cramped confines of a ship. If you combine that reactor with electric thrusters, you get a hybrid system capable of running for over a decade without ever needing to refuel. The objective changes from just surviving a trip to establishing a permanent presence. Sustained, multi-year orbits around massive planets like Jupiter suddenly become practical. Instead of a quick flyby, a nuclear electric probe could spend years dipping in and out of its radiation belts and icy moons. The vast empty stretches of the deep solar system, all the way out to Saturn's rings and beyond, become accessible. Nuclear density makes the outer planets reachable within a human career. But how do you completely defeat the rocket equation? You leave the fuel on Earth. This is a model of a solar sail. It carries zero propellant. Instead, it uses the momentum of photons, particles of light, to push the reflective material forward, creating thrust with no exhaust. Researchers are currently testing ways to point powerful Earth-based lasers at larger versions of these sails. A concentrated, continuous beam of light could accelerate a probe to a fraction of the speed of light. Questioning the need for traditional fuel has also opened the door to fusion propulsion, which could potentially drive a craft to 10% of the speed of light, fast enough to reach neighboring stars in decades rather than millennia. Reaching another star requires a total departure from how we currently think about spaceflight. We have to stop carrying physical mass and learn to surf the interactions of light and plasma. Aerospace is undergoing a massive transition. The industry is moving from relying on volatile explosions to precision electricity, swapping short bursts of speed for continuous momentum. That chemical rocket launch is the final refinement of a legacy technology. We have nearly reached the physical limits of what burning fuel can achieve. Because engineers have figured out how to sever our reliance on heavy fuel tanks, Aiming a probe at another star is no longer confined to science fiction. By solving the mass problem through light seals and fusion, the jump to another star system has moved from a theoretical dream to an active project. We aren't just wondering if it's possible anymore, we are drafting the flight plans.